So here we'll try to solve this problem of this Truss problem. You just see it has two member 1 and member 2. An angle is given here. Okay, 30 degree. This also 30 degree. Length is 5 meter each, and your material property is of 200 GPa, and your area is 0.0005 meter square. So basically, you consider B 50 mm and D your 10 mm. In that case, the area will be this one. Okay. And the boundary condition is given here. Both N are hinge. Okay. So we have 4 unknown U1, 4 unknown. Okay, so here we'll have this support, this support, this support, and this support. Okay, so displacement at the degree of freedom 3, 4, and 5 and 6 are 0. Okay, so we have now 4 unknown, and we know we have 3 equation of equilibrium. So this problem cannot be solved using your equation of equilibrium. Okay, because this is your indeterminate problem. Can be solved. It cannot be solved only. It cannot be solved. It cannot be solved only using the equation of equilibrium. Okay, so here we'll see how we can use our stiffness approach to get the solution of it. So to find the solution of this type of problem, what you have to do? First, you have to identify what is the node number, what is the global node number, and the corresponding degree of freedom. So here I have chosen node number 1, this is 2, and this is 3. Global node number is 1, 2, and 3, and the corresponding degree of freedom is 1, 2, 3, 4, and 5, 6. So we have total 6 degree freedom for this Truss problem. So we will have 6 by 6 size matrix, global size matrix, KG matrix will be of 6 by 6 size. Okay. Now here the node numbering here, we just see what I say. You can choose their own way. You can choose your own way to give the node numbering, but you should be consistent with that. Okay. So you can choose node numbering. You can consider this is node 1, this is node 2, this is node 3. Okay. Or you can choose this is 1, this is 2, and this is 3. Like that, you can choose your own node numbering, but you should be consistent with your global node numbering and its corresponding degree freedom. Okay. So here what I am going to do, I am going to consider this node numbering. Okay. Now once you identify node number and global degree of freedom corresponding to that node number, okay, you also have to find the local node number and its degree of freedom. Okay, so for element 1, global node number is 1, 2, 3, 4. Okay. Now if you see local node numbering, you can consider this node as a 1 and this is your 2. Okay. So global, so local degree of freedom only 1, 2, 3, 4. Okay. Now once we calculate that your K matrix, and if you do the T transpose KT, you will get the K matrix of this element 1. You will get the K matrix of the element 1 according to this local node numbering. Okay. So once we get that K dash matrix, that basically that K dash matrix here will be of 4 by 4 size, because each element have 2 degree freedom. So there is total 4 degree freedom for element. So it will be a 4 by 4 size, and your corresponding local degree freedom will be 1, 2, 3, 4. Okay. Now if you see, also identify local node numbering and corresponding degree freedom, and you have to obtain the stiffness matrix. Once you obtain the stiffness matrix based on your local node numbering, okay, based on the local node numbering. Now, if you want to find the global stiffness matrix using that matrix, using the local matrix, okay, using that individual element matrix, in that case, you have to follow this sequence, okay, and you have to always maintain. You have to always be consistent with that. You have to always be consistent with that. Then only you will get your result. Okay. So here, see now, if you see that angle, So here you just see, I consider this is your first node, local first node, and the second node, and angle is given here 30 degree. So here angle we always consider anti-clockwise. Okay, angle you always consider anti-clockwise angle as your positive values. Okay, so here this angle is 30 degree. So we will consider this 30 degree angle for this element. Now, if you consider the second element, in that case, you can consider this is your local first node and this is a local second node, and here your angle will be 150 degree. Okay. Now, if we consider this is a local first node, this is local second node. Okay. So you have to consider this angle. Okay, for your calculation. Okay. Now here, what we have done, we have considered this is our local node 1, this is our local node 2, and we have obtained our stiffness matrix considering this angle as 150 degree. And since this is your local node 1, this is local node 2, and corresponding our global node numbering, this is 3, and this is your 1. Okay. So if we obtain your K2 dash matrix, okay, if you obtain your stiffness matrix, you obtain stiffness matrix of the second element, K2 dash is equal to T transpose K2T. Okay, so if you obtain that if you obtain that K2 dash matrix, okay, so our local numbering will be 1, 2, 3, 4. There also 1, 2, 3, 4. But global degree of freedom will be 5, 6, 1, 2. So here you write 5, 6, 1, 2. You also write 5, 6, 1, 2. Okay. So this is your local node number 1, local node 2. But global node numbering is 3 and 1. So corresponding degree of freedom will be here 1 and 2, 3 and 4. Here it will be 5 and 6. Here will be 1 and 2. Okay. So whatever the component will come here, whatever the component will come here, that will go to your global 5 by 5 position. Okay. Similarly, whatever the component will come here, that will go to global 5 comma, that will go to global 6 comma 5 position. Whatever the value will come here, that will go to the 1 comma 5 position. Okay. 2 comma 5 position. Okay. Similarly, for the second column also, third column, fourth column also, you have to find what is the location of it, and you have to basically obtain your global stiffness matrix for considering this position, considering the value. If you consider this is the node 1 and this is node 2, okay, then angle you should consider this angle as a positive angle. Okay. If you consider this side, then angle you should consider as a negative one. Okay. So here for this element 1, for this element 1, okay, so you either you can consider this node numbering 1 and 2 like this, or you can consider this node numbering 1, 2 like that. Okay. In that case, you have to consider this angle for your calculation. Okay, this angle theta to calculate your transformation matrix. This angle theta, okay, that positive value, it is coming to 110 for calculation your transformation matrix. Okay, so you can use either local orientation as like this or like this, both the way you can do, but you should consistent while calculating your global matrix from that local, while deriving global matrix from your local matrix. Okay, you just see for the element 1, we know the general equation for stiffness matrix. Here that is equal to AE by L, 0 minus AE by L, 0, 0, 0 minus AE by 0, AE by L, 0, 0, 0. Okay, like that. Now, if you want to find our, but this stiffness matrix represent, the displacement and force quantity along the local axis. Okay, along the local inclined axis like this. Now, since we can do by doing T transpose KT, because if we do the T transpose KT, we can obtain our K matrix. So here we are considering element 1. We can obtain our K dash matrix. We can obtain our K dash matrix. Here we are considering element 1. So K dash matrix for element 1 will be like this T transpose KT. So here transpose matrix we know. Okay, transpose matrix we know. If you multiply KT first, okay, and then whatever the value we are getting, here, okay, you multiply with the T transpose matrix, you will get that your A1 dash matrix. That is according to our global orientation, okay, or global axis system. So if you do this multiplication, you will get our K1 matrix is like this along our global axis system. Similarly, we can obtain our global stiffness matrix for the element 2. Okay, so it will be T transpose K2T, T transpose K2, T transpose K2T. Okay, T transpose K2T. If you do, you will get K2 dash matrix. Okay, so you will get the K2 dash matrix. Okay, that is our according to our global orientation. According to our global orientation. Okay, now we have to fill your stiffness matrix. Okay, you have to fill your, now we have to obtain global, stiffness matrix, KG matrix. So here you just see the size of the global stiffness matrix will be 6 cross 6. Okay, and local have 4 by 4. Okay, now here you call our local was 1 2 3 4. This is also 1 2 3 4. Okay, but global was 3 4 1 2. Okay, so whatever the value 1 1 was here, that will go to the corresponding 3 3 position. Okay, so here you see this time to 3 3 position. Now you just concentrate of the column. Now you consider this column. Okay, so second element 4 comma 3, address of the second element, this value will go to 4 comma 3. So 4 comma 3 you try to find 4 comma 3, 4 comma 3, we are getting this value. Now this is your the next position here. This is corresponding to 1 3 1 3. So we just try to find 1 and 3 like this. So initially we got 3 3, then we got 4 3. So we are getting 1 3. Next it is your 2 3. So next it is your 2 3 2 3 like that. Okay. So whatever the value initially got in the first column, okay, you just see we got it in the third column. Okay, but again you have to see that this 0.75 is corresponding to 3 3, so it should be here 3 3. Okay, directly you should not take this column and should not replace it here. You have to find the corresponding, find the value corresponding to your degree freedom. You have to find the value corresponding to the degree freedom. Okay, now if you consider the second column, okay, now if you consider the second column, is your 3 4 value is 0.433. Okay, so here you just go to 3 4. This will is your 4 value is your 0.25. 4 is your 0.25. Next is your 1 4 1 4 1 4 is your 0.433 and 0.25. Okay. Similarly, you have to take this column and you have to find location of individual component and you have to fill it in global stiffness matrix. Okay. Now if you go to the second element, okay, now if you go to the second element, okay, so angle we have considered as a 150 degree. Okay, so if you consider angle 150 degree, and then we have obtained our K2 matrix, then we have multiplied T transpose KT, we have obtained K2 dash matrix. So this is your K2 dash matrix. Okay, now this K2 dash matrix you have to fill into your KG matrix. So already this part you have obtained. Now what do we do? You have to fill this K2 dash matrix. You have to take this matrix and you have to fill it here. You have to take this matrix and you have to fill it here. Okay, to fill it here to obtain your global stiffness matrix. Now here you just see, consider this column. First address is 5, you just consider this first element here. Address of this element is 5, so here we just see 1 2 3 4 5 6. Here 1 2 3 4, 5, 6. Okay, so 5, 5. You have to find 5, 5 position here. 5, 5 position here is your 0.75. Next is your so 6, 5 is your 0.33. Next, this is 1, 5. 1, 5 is 0.75. So 1, 5 is 0.75. And next is your 2, 5 is 0.43. Okay, so you have consider this one and we have to fill it here. Okay, so this fifth column initially local degree freedom was 1, 2, 3, 4. Okay, this column will come here, but again we have to see the address. You have to see the degree of freedom. You have to see the corresponding location in the global stiffness matrix. Okay, now if we consider the second column, okay, so this address is 6, 5. So 6, 5. So 6, 5 is minus 0.33. Now this address is 6, 6.25. So 6, 6 is 0.25. Next we have 1, 1, 6. Okay, 1, 6. This address is 1, 6. 0, 1, 6. 1, 6. If you see, it is 0.33, and this is 2, 6 minus 0.25. So like that, we will fill. Okay, now if we consider this column, so this is your 5, 6, 1, 2. So this one is corresponding to 5, 1. This is a 5, 1. So here 5, 1, 5, 1, 5, 1 is 0.755. Okay, next is your 6, 1. So 6, 1 is 0.433. Okay, now here is your 1, 1. 1 value is 0.75. 1 value is 0.75. Already we had some value. Now again we added it. And next is your 2, 1 is point. This is 2, 1 is 0.433. Okay, so you also consider this one and we fill it here. Similarly, we have to do for this column also. Okay, now what we have done, we have considered K1 dash matrix and K2 dash matrix. Okay, and we have obtained KG matrix. Okay, so once you obtain KG matrix, now what we have to do, we have to go for the solution. We have obtained our stiffness matrix for individual element 1 and 2. Thereafter we apply transformations and then we obtain our global stiffness matrix. Okay, now what we are going to do, we are going to solve the problem. So here you can see the boundary condition. We have the degree of freedom 3 and 4 and the 5 and 6. So here we have to consider while solving the problem. Now how to apply the boundary conditions? We have to apply this constraint. So we can solve various way. We can solve it in various way. But here I will discuss. I can discuss two approach. One approach is that we will apply some extra stiffness on the restraint degree of freedom. Okay, so here you just see this point is restraint and this node is also restraint, and correspondingly degree of freedom 3 and 4 are restraint. Since this is restraint, that indicate that there is a deformation is almost zero, or displacement of this degree of freedom is almost zero. So you also can achieve that condition if we increase the stiffness corresponding to this degree of freedom. Okay, corresponding to this degree of freedom here. Okay, so if we increase the stiffness such a way that displacement coming in this corresponding degree of freedom is almost zero, then we can say that is a restraint condition. Basically, what we are doing here, we are assuming a spring and we are applying the spring constant such that displacement at this node, displacement at the degree of freedom corresponding to this node is almost zero. Okay, so now we are going to see how we can obtain it. So here you just see this is the global stiffness matrix. This is the global stiffness matrix that is your unconstant. Okay, now we want to apply the boundary conditions. Okay, so how we are applying the boundary conditions? Here you can see we are applying the boundary conditions on the corresponding degree of freedom here. However, increasing the our applying the boundary condition, we are enhancing the stiffness by 10,000 times. Enhancing the stiffness by 10,000 times. We are only enhancing the stiffness only in the diagonal terms. We are only enhancing the stiffness only on the diagonal terms. Here you also can see here this corresponding to third and fourth, and this is corresponding to fifth and sixth. Okay, here also you just see we are also enhancing the stiffness by 10,000 times. Okay, so now if you increase the stiffness by 10,000 times, so our stiffness matrix look like this. So here this stiffness matrix will increase. Initially it was 5 to the power 6, 5 into 10 to the power 6. Now we have 5 into 10 to the power 10. Similarly, for this point also, here you can see initially we had 1.5 e to the power 7. Now we have 1.5 e to the power 10. Okay, now here you can see we have applied the boundary condition, the corresponding degree of freedom by increasing the stiffness on the diagonal terms. Okay. Now what are we going to do? We are going to solve it. So here we are going to solve it. This term will be 1.5. This also should be 5, 10. Okay. So this is the our stiffness matrix with a constant condition, and we have to see at which point we have applied loading. Okay. So we have load at the degree of freedom 1 and at the degree of freedom 2. Now again you just see if this is your positive value, then this should be positive, but here load applied in opposite direction, so it should be minus 20. So here our loading is the first degree freedom and the second degree freedom, and rest of the degree freedom we have 0 value. Now we know that solution for the static problem, that is your Ku is equal to F. Now we can obtain our displacement by taking inverse of K and by multiplying with the force vector. Okay, now if you multiply, you will observe that you are getting displacement quantity like this. You are getting displacement quantity like this. Here you can see at the degree freedom 1, 2, we have the value that is your 3.33 e to the power minus 7 and 2.6 e to the power minus 6. And here also you can see at the degree freedom corresponding to 3, 4, and 5, 6, which was constant, we are getting a displacement in the range of minus 10. Okay, so now here you can see displacement in this degree freedom is very negligible in comparison to the degree freedom 1 and the 2. Okay, so this is the way you can get a solution. Other way is that row and column elimination technique. Other way is the row and the column elimination technique. So now here we will try to find what are the forces are acting there, what are the forces acting there. Again, we know that we can find the force. It should be 5 to the power 10, that is 1.5. So now here we can solve it to calculate our reaction forces acting in each member. Okay. So now we know the displacement quantity, we know the stiffness. We can multiply these two. We can find how much forces acting there. Okay. Now if you multiply, you will obtain the forces like this. Okay. So here you just see at the degree of freedom we have 10 and minus 20. That is your applied loading, and here we are getting the reaction forces. Okay. Since loading is not symmetric, so our reaction forces will not be symmetric. Yeah. Here you can check your calculation by adding this value and this value. It should be your 20. Okay. And you should add this value and your this value, it should be 10. Okay. So minus 1 will be there, that represent if this is positive, then this side will be negative. Okay. So if you add these two value, which is corresponding to your horizontal degree of freedom, that value should come as 10. So this way you can check your calculation. Okay, whether your calculation is correct or not, okay, that you can check. Now, next what we are going to do, we are going to solve by row and the column elimination technique. So here we know this is our global stiffness. Now we have to see which are the degree freedom are constant. So here we have constant degree freedom is 4, 5. We have constant degree freedom is 3, 4, 5, 6, 3, 4, 5, 6. Okay, so what are we going to do? We are going to eliminate that particular row and the column. Okay, so third row we have to eliminate. So we have to eliminate third row and third column, and your fourth row, your fourth column, and your fifth row, fifth column, and sixth row and sixth column. Okay, now this matrix we have left. Okay, so our K matrix after constraint, that is your 2 by 2. Now similarly, we also have to apply the restraint condition in our force vector. Okay, that also you have to eliminate. Okay, now this is our K matrix, and we know that K du, that is equal to force. K matrix is a 2 by 2 force vector, also you have 2 by 1. You have 2 by 1. Okay, now you can solve it easily. Now if you solve it, you can get this value. Okay, so now here you just see this value is very same to the value we obtain using applying your additional stiffness on the restraint degree freedom. Okay, now what are we going to do? We are going to find the reaction forces. So now we know that stiffness matrix, and we know the relationship. So we know that K U, that is equal to force. This force basically include your applied force as well as your reaction forces. Okay, so since we know how much displacement is coming, we can put the value here. Okay, so we can find what is the force vector. Okay, so we have K matrix, and now we have displacement vector. We multiply. Okay, so here we just see these value are 0. To multiply, you will get this force vector. Okay, now again you just see summation of these two will be 20, and this one should be 10. It is minus 10. That means this side positive force that was acting there, and reaction force minus 10 here. Okay, so this we can also verify. Now here if we try to compare, we just see this value we get by applying additional stiffness, and this one we obtain by row and column elimination technique. Okay, here you can see that force vector coming here and force vector coming here are very same. We have some value on the third decimal point, so you can see both the method is showing good accuracy. Okay, now if you see the displacement here and here both are the same. Only in the case of first method we are getting some value here, but that value is very nominal, that is less than 1000 times. Okay, so here you can see if this is your 6, it is your 10. So basically less than 10,000 times or 1000 times. Okay, so in both the method is equally applicable. Main problem is here. In this case, you have to solve it your 6 by 6 matrix. So manual calculation will be very difficult. You have to write some computer coding for that. Okay, and this one we can solve by hand calculation, because at the end when we apply the boundary condition, at the end it is coming 2 by 2 matrix. So inverse of 2 by 2 is easy, and we can do it by hand calculation. Okay.